Hello everyone, I'm Alessandro from the 35th PhD cycle in energetics, and today I'm going to present you my research on latent heat thermal storage so far. This is just to give you an overview of what I'm going to be talking about. I'll start with the gaps I have found in the existing literature about the latent heat thermal storage, which is called LHTS in short. Then I'll move to the modeling framework I have adopted and its results, and finally some future perspectives. Regarding the research gaps, there are two main issues that I found interesting to address. First, shell and tube LHTS units are often modeled as a cylinder made of phase change material crossed by a single tube of water. The extension to larger storage sizes is often carried out under the hypothesis of periodicity, which is not suitable as can be seen from the figure. Second, very few articles focus their attention on the operations of latent heat storages and their integration in medium and low temperature processes. Hence the research question. How can we characterize the behavior of a multi-tube latent heat thermal storage at a system level? I started considering a reference shell and tube design, where the pipes have longitudinal fins and the whole storage is the assembly of repetitive elementary units. In order to obtain a model for this reference configuration, I first reduced the computational domain exploiting its geometrical and physical symmetries. In particular, the compactness of the considered configuration allows to neglect the effect of natural convection in the liquid PCM. Consequently, I created a two-dimensional CFD model with Fluent, where the governing equation is purely conductive. Finally, from its results, I extracted a 0D mathematical model that expresses the time-dependent thermal power of the storage as a function of only two parameters, its initial and current states of charge. Hence, I obtained a bundle of characteristic curves for the thermal power released by the storage during discharge. As said, the power output depends both on the current and the initial states of charge, and the 0D model in dashed lines approximates very well the curves of the 2D model in solid lines. As you can see, similar considerations are valid for the charging phase. Therefore, the 0D model can be applied, for instance, to estimate the performance of a latent heat storage at system level. Here, the results show a consistent district heating morning peak reduction following the deployment of the storage. To conclude, I think there are three main future perspectives to address. First, the temperature at which hot water is produced by the storage has a pivotal role on system integration strategies. Thus, further research must be carried out in this area. Second, a reliable 0D model could be profitably used for controlling the storage, but also for its simulation in commercial software like Simulink or Transys. Nevertheless, experimental studies are fundamental for the validation and calibration of this compact model. So that's my research in a nutshell, and thank you for your attention.